Welcome to the exercise number 8 of the lecture Pattern Recognition and Machine Learning. Today's topic is hidden Markov models. At first, I will start with a small review of hidden Markov model. I will explain some of the basic idea of the hidden Markov model. Afterwards, I will answer some of the comprehension questions, and at last I will show you some Python code that you can solve on your own, and afterwards we talk about the solution. Let's start with a small introduction to hidden Markov models. So what are hidden Markov models? Hidden Markov models are like GMNs in the sense that you analyze a probability distribution of multi-dimensional data. The only problem with those things are like Gaussian mixture models is that they don't have a sense of time in it. So the temporal progression was assumed to be uncorrelated. If we know that this is not the case, an example for speech, we don't have a temporal, we have a correlated temporal component because our sounds that we make are some sort of correlated. We need some sort of a temporal behavior. This is solved in this case with a Markov model. So we have a Markov model or Markov process that models our different probability distributions. Each of those probability distributions are one state, and if we look at our diagram, we have those states in the circles here with S and a number. In this case, we would have, for example, 5 different states, and those states are the hidden part of our Markov model. So if we observe an output, an emission, in this case those B vectors, we don't know from which of those states we have the emission. Those states are hidden. What we also have is for each stage a probability, transition probability. Those are those arrows with the coefficient in it. In this case, the A33 would, for example, be the state or the probability that we have the state S3 and we leave it and transmit to the another state at 3. In this case, we would just stay in the same state, but the other arrows, for example, this arrow would be from state 2 to state 3, would be the probability of those changes of states. So what we can see here is that our hidden Markov model is fully described by by the number of states, the A matrix and the B matrix. So if we know pretty much A and B, we have the whole Markov model, the whole hidden Markov model designed. The number of states is pretty much in those A and B vectors because the number of states describe the size of our matrix. Now we can look into a little bit more detailed version of a hidden Markov model. This has the constraint that we only allow transitions from the left to the right. So only transition changes from one state to an upper state or itself. So an example, this state change is also allowed. With this constraint, we can make some assumptions about our A matrix. Because we know that only transitions from left to right are allowed, we can say that our A matrix has to be some zeros in the lower left side of the matrix, because those transitions are simply not allowed. A more constrained version of this left to right version would be a linear HMM, because now we only allow transitions also from left to right, but also only to the next state. So jumping over one state, this wouldn't be allowed. This will also let us make some assumptions about our A matrix, because now we know that the upper right side of our matrix also has to be 0. Now we have defined our hidden Markov model as a structure, but it doesn't really contain the time component in itself. For that we would need a Tredis diagram, for example. In this case we use a Tredis diagram with 6 different states, and we can model there our input and our observable data and our probability transition in it over the time. So at first we would start with x0 and in the state s1, because this always has to be our first state. So our transition probability on the left here would be a01, so the transition from state s0 to state s1 is a01, and this always has to be 1, so we start in the state s1. This is shown with this diagram, or with the circle. Afterwards we can model our next possible state. So if we look at our hidden Markov model on the left, we can see we have a special probability that we stay pretty much in the same state. So this would be a11, this part. And in this case, another option would be a12. If we use this transition probability, we would go to the second state. This would be here, so the second version would be here, 1, 2. And we can also see that there's a third transition probability to state S3, and we can also draw it here in the states. This would be A13. So only these 3 states are allowed at the second time step, because we don't have another option to go to a different state accordingly to our HMM. If we do this for all of the time indices, we will get a very confusing and big diagram that is called the Tredis diagram. And I will try and show you the result afterwards. It looks something like that. So this shows all probabilities or all possible transition states in those 9 time steps that we can have accordingly to our HMM. If we look more closely to those Tredis diagrams, we see those dots, and those dots will represent our output of our observable data. So those are those emission coefficients BI of x. Those coefficients are the output of our, for example, GMM. If our HMM consists of GMMs in each state, so each of those states would be an own GMM. The output BI would be the output of just a normal GMM with the input vector x. So you can just imagine those states as normal GMM models or GMMs, and the output B's as the output of those GMMs. Okay, now we can have a look at the decoding problem or the Viterbi algorithm. For that we need to do at first an initialization. That's the first step of the Viterbi algorithm. For that we just write the probabilities for the first state. Afterwards we begin the second part of the Viterbi algorithm, which is the recursion part. For that I've drawn here this first part of the Tredis diagram, and we see that we have the first parts in it. What we want to do is we want to calculate the most probable way to get from one state to another. For that we look at each of those transition probabilities. For, in this case, the first state S1, and we look at all of these variables and look which of those has the highest probability. And the important part is that we don't only look at the transition probabilities itself, but at the multiplication with the previous probabilities in that case. So we look at the whole way to this new state, and from all of these four possible ways, we look at we choose the one with the highest probabilities. In our case, or in our example, maybe the first one. So we have to get to the first state only the first transition probability. Afterwards, we can do this for the second part as well, or for the second state S2, this state. For that, we also have to look at all possible ways to get to this state, and we have to choose the one with the highest probability. In this case, it would be, for example, the third way to go to that. And with this method, we can do this for the whole time, for the whole timeline and the whole states. So when we are pretty much finished with the recursion state, we have the termination state. And in the termination state, we know that we leave our Tredis diagram in a certain state. So this is a third state, and the last state would be then the backtracking. So we now have all the probabilities and the probabilities of the different state transitions. And what we now want to do is we want to apply this backwards. For that, we just go from our end state where we know we pretty much landed afterwards, the way back, and we always choose the way with the highest probability. And this way we know our route back to the state, to the start state. And we can just look at the states that we've chosen. So the last state would be S4, and then always S3 to the initial state. And this is our estimated state propagation. So let's go to the second part of this exercise, the comprehension question. The first question would be, what is the common concept of GMM and HMM? What is the difference between the concepts of GMM and HMMs? So GMM and HMM are in principle similar in the sense that both model the probability distributions of multi-dimensional data vectors. And the difference between those is that the HMM also models the temporal progression. So the GMM is a more basic version that has the assumption that we have uncorrelated time component in it. So we don't look at the time component. And the HMM can consist of multiple GMMs. And if it consists of multiple GMMs, we model therefore the time component in it. So if you have different states that represent a change in time, and different GMMs that assign to those time changes. So the second question can also be answered with this slide. The question states as follows: describe the basic functionality of a HMM using the diagram on slide 14. Which quantities determine the expected output length of the HMM? So we can see we have four states: one initial state, one final state. We have some of those transition probabilities, so there are some of the A coefficients. And we have two emissions. We have only two emissions because we only have two GMMs in it, because the initial state and the final state don't have an output. The length of the HMM is defined by the transition probabilities. If we would, for example, have a lot of ones, or if we have ones in it, for example, A10 is a 1 and A13 is a 1. All of the other states, A02 and so on, and A12 and A11 has to be 0. if this would be the case, we would go from the initial state to the S1 state and afterwards to the final states. And we would do this always, always, because the transition states are 1. So the length is pretty much determined by the numbers or by the probabilities that are in those transition coefficients. If they are close to 1 or closer to 1, they are that means that the whole hidden Markov model is probably shorter than others. The third question is, which two matrices determine the characteristics of the HMM in a unique way? How is the HMM model lambda thus defined? This is pretty easy to answer because I already answered that pretty much. So we know that our HMM model is defined by the two matrices A and B. A are the transition probabilities and B are the emission probabilities, and therefore our model lambda is fully described by the two matrices A and B. The next question is, what is forward probability? Describe the forward algorithm in a few words. Explain shortly the three main parts: initialization, recursion, termination of the algorithm. Could the algorithm also be applied backwards? So for that, let's answer the first question. What is the forward probability? The forward probability is the probability that after n time steps, the HMM is in the state Si and generated on the way the feature sequence X of n. So we can write this also in a formula. So the forward probability Fi of n, so the probability of state I and in the time step n, is the sum n minus 2 j equals 1, n minus 2 because we have these two extra states, initial and final state, and therefore we subtract minus 2 and start at 1 of our forward probabilities before, n minus 1, so of the state j at the time step n minus 1, so the step before, times the current transition probabilities aj dot I times our emission probabilities, and those emission probabilities are dependent on our observation sequence x of n at the time n. And this is the forward probability, and we can apply this algorithm backwards. This is the idea of the Viterbi algorithm, where we use backtracking to solve this problem more efficiently. So the last question is, describe the Viterbi algorithm in your own words. Can you refer to slide 32? What meaning does the variable ti of n have? So this is a screenshot of the slide 32. As already described, the Viterbi algorithm has pretty much three phases: the initialization phase, the recursion phase, and the termination phase. And afterwards we can do a backtracking to reconstruct the optimal path. So for this we already discussed the initialization phase, where we have the first calculation of the first initialization states. Afterwards we do a recursion, where we calculate the path with the highest probability to each of those states. These are the black arrows here, and this is done for all of the time indices. So each of those time indices has their own calculation. And afterwards we do the termination, when we know we are in the last state, and go to the final state. And afterwards we have this nice map where we can use backtracking, where we start at the final stage and go backwards and reconstruct the optimal path. Yeah, let's start with the last part of this exercise, the Python demonstration. For that, we provide you a folder. In that folder there are a lot of files, and you can open the task PDF. The task PDF you will find 3 topics. The first one is remarks, decoding, and evaluation. In the first part, there is a description of the dataset we provide you with. It's from Hamburg, Munich, and the Brocken, which is a mountain in Germany. The weather data from that 3 places in the month of July. So 31 data set points as a time point, and each of those days has 3 numbers in it, and those are the degree in Celsius, maximum degree, maximum temperature, the rainfall in millimeters, and sun hours. So the data set describes just weather data from 3 places with 3 different kind of measurements. There are also states that we define: the initial state, the sunny state, the cloudy state, and the rainy state, and the last one, the final state, in which we want to classify our data. And the first example would be the decoding. So we want to reconstruct the state sequence from our observed data. So we load in our models and want to reconstruct our states. This is done in the first part is done in the DIY HMM exercise decode DIY Jupyter notebook, which you can open and try to solve. I will go through that in a minute. And there you have to just fill in some, I think not much code. And the second part is the evaluation, where we want to look at the observed sequence X, and we want to look how close that sequence is to a recorded weather data in Hamburg, Munich, and Brocken. So we want to find the best match from our observation to a given model. The 3 given models are the 3 places. And there you can also have a look at first in the DIY part of this exercise. And I will go through the first part, the decoding DIY part now. Let's start with the first exercise, the decoding exercise. For that I will go through the DIY version of it, and afterwards I will talk to you or with you about the solution. If you want to install the first packages, NumPy and sklearn, you can do it with our requirements.txt, so you can do it in a virtual environment, for example. Third part here is we load our predefined models. So we have provided you with some NumPy objects, and that they can be loaded in with NumPy. If we do this, we have our models. So we have an HMM model for the Brocken, for Hamburg, and for Munich. You can look at those if you want to. With this, we insert a new cell and have a look at the last A, what was that, and run it. So our A from the transition states of Munich are just two arrays, and the reason for that you can look up in the task PDF. So we have 2 transition states because we need to define that model that we have only 31 states, and afterwards we don't have any more transitions. So that's for that. And if you have a look at B, we'll see that B contains some Gaussian mixture models. And if you want to look or to learn about those, you can have a look at the sklearn library in the Gaussian mixture models. Those are objects from that package. So now we've defined our 3 Gaussian, hidden Markov models with those provided data. And afterwards we can have a look at some predefined data, for example this transition state vector. So it's a definition. It's a function where we just generate a random number of this between those ints. So we have as an output just one of those numbers. Afterwards, we have a function which generates a sample from our from a weather model, and that will be used for generating our own sample weather model. I will talk to you later about this. The next part is an HMM sample month. This uses both of the functions before. So in this part we create our own weather data for a full month, which provided models. So if we put one of our HMM models that we generated before in our function, we will get weather data for a full month with this model. So we have pretty much a machine that generates artificial weather month with a given model. Afterwards we can come to the decoding problem. So for that we use the Viterbi algorithm, and the task that you have to do is to we have to run this cell as well. The task that you have to do is to complete the Viterbi algorithm with the function decode. And the idea of that is that we give in an HMM, a hidden Markov model, and an observation, and we want to look into what sequence is likely the sequence that generates that observation. So for that you have to fill in some of the red question marks here. But before I will go through the part where the first one starts. So at first we want to get our transition matrix, that is HMM of 0, 0, because it's defined beforehand. Afterwards we want our termination transition vector in this case, and our observation model. So that are all given by the loaded data that we have loaded before. Afterwards we want to define the dimensions. So for example, we know that n needs to be the length of b plus 2, and t is the length of the observation data, and so on. Afterwards we want to create some empty vectors, for example, or matrices, arrays. The probabilities v, they have the size of the length of our data set, so overall, the length of our states, so 5 states, and the length of our data set, 31 days. And the same vector size has the states vector. Afterwards we create a vector for our estimated sequence. So Q is our sequence that we is the sequence with the most probability that those states generated that observation. And afterwards we create a temporary variable that we will fill in over time, and we only use for just temporal reasons. And then the big for loop starts. At first we iterate over all observations, so n is our observation counter if you want to, and for each observation we want to go through each state, that is I in our case, and we start at the very first observation is the initial state. So we have this if clause. If the first state is 0, we want to do something special with the data, and we know that the first if the first data is the initial state, we know that the states are also 0 for that case. So we need to fill in our vi of n is something times our exponential function. So we need to fill in our a. In the other cases, if we don't have the very first time indice, we go in this for loop or in this else clause, and especially in this for loop, and there we go through each of the states that we have left. So we multiply our previously generated probabilities times our transition matrix and get our temporary variable. Afterwards, we have filled our temporary variable, and we want to search for the most probable transition of this vector. So you need to fill in the missing part of it. Afterwards, we can just search for the maximum and do this for all the full loop over all iterations, over all states, and so on. Afterwards, we can just terminate the state, so we know the optimal path, and we can have a look at the last observation state. There you have to fill in this as well from the temporary data that we have in the terminate state, and calculate the corresponding path probability. And the last part would be to do the backtracking when we think in the Viterbi algorithm. So we provided all of our paths with the maximum probabilities, and now we want to do the backtracking of our path. So we need to go the reverse direction and search for our estimated the most probable paths, and that fills our queues. And afterwards, we just return our queue as a vector and have the estimated states that we calculated via Viterbi algorithm. So for that, you can fill in the question marks, and you have to, you can do it on your own. I will talk to you in a minute about the solution. So the first question was to fill in these two question marks, and we have the case that we have the initialization, so it's the first time step that we are looking into, and we want to fill in the probabilities for the first time step, so for the state I and the time step n. So for that, we know that our A, which consists of our first transition state, needs to be in the zeroth initial state, so there's a 0 in it, and in the ith state, so we go from in the first time index to the index of those values. So this would be the first line. Afterwards, we know that the states have to be 0, so we fill in the 0. Yeah, the second more or less question was to fill in those temporary values. So now we are in the case that we don't have the initialization state, but pretty much everything else, every state besides that initialization state. So we need to fill in V were on our probabilities. So the first index is again the time index, but the time index of J. So we loop through each of those time indices again, and each of those states indices, and need to fill in the Jth indices. So we multiply the J's indices by the previous time step. By previous indices, so n-1. Okay. n-1. And we multiply it with a's, so those are just the current versions, so the j and I state. So this is pretty much the Viterbi algorithm that we want to multiply all of our previous states with the transition states A, and get a value for each of these new states that we go into. Afterwards, we have a vector temp that consists of n values, n minus 2 in this case, because we don't have the initial value, the final state, of course, so n minus 2 values. And afterwards we need to find the most probably input of that state. So for that we have those this argmax numpy command which will find the position for the most probable value of the temp value. Afterwards we can calculate the corresponding maximum output probability of this node. For that we use just the max argument, which is pretty much just the same element, but here we have the argument of it, and here we the value itself of that, and multiplied with the exponential that we have here before, so the e to the power of b minus 1 times the rest of it. So this would be this case. And now we have our state path probabilities. So for each of those we have a number. Afterwards we have the termination. There you didn't have to enter something. And now we have to enter the last observation state, the most probable observation state. There we have to do pretty much the same as in these two lines. So we have to, in this case, we want the indices. So we have to calculate the argmax of it. And here we have the maximum, the element itself of it. And yeah, now the last question mark was in the backtracking. So we want to do the backtracking from original transition into the final state. So we have here the case that we have the end of of our observation, and we want to go back. So in this case we don't have to do anything, and in this case we have to use real backtracking. So we have to use the previous, or in this case next value, because we're going backwards. So q of n plus 1. The plus is in this case the double reversed previous state. So normally you would use n minus 1, but here we go backwards, so we have the n plus 1. And this should be it. We should now return our decoded sequence. To test that, we can create our artificial observation. So we can use, for example, in this case, HMM of M. So it's, I think, it should be Munich, the model of Munich. If we, I think we have to run this set, yeah, no errors. Afterwards, we can run the sample month of Munich, and there we have a lot of data. So we have, for example, these are the 3 generated units. So the first one is the maximum temperature. It's around 20 degrees to 30 degrees, something like that. Afterwards, we have the rainfall. That's pretty low, from 0 to, I think, 13 millimeters, 25 millimeters. And the last part would be the sun hours. So on Sundays we have 13 hours of sunlight, 14 hours of sunlight. And other days we only have 2 or 0.9 hours of sunlight. So we generate this in a random fashion, but they are based on the Munich hidden Markov model. In the last line we have the real state sequences. So these are the sequences that we have going through to generate that model. Now we can come to the last part, which is evaluating our estimated sequence. So for that we use our previously written decode function, which uses the Viterbi algorithm. And what we want to do is we want to put in our observation that we estimated, or that we created before with our HMM model. So we have our observation, which is what we really see, those are the rain data, and the real states, or the states that we used for generating this data. So what we want to decode is our model that we want to look if this is a good fit or not. So we can insert for the first version, for example, our Hamburg model. so our HMMH, from which we know that this is not the best fit or should not be the best fit. So afterwards we want to get the accuracy. So for that we use, because we want to use accuracy, we multiply with 100, and afterwards we use the sum of our D states. So this is the states that we estimated are the states which are used for generating our model, for generating our observation with that given model. So if the difference of these estimated states and the real states are 0, we know that they are correctly estimated. So if we sum up over those correctly estimated version, we get a high number, and this number is in this case the length of our data set, so 31 days, so it should be 31 values. And we, because we want to use the estimate, we divide by 31. So if we would estimate our sequence correctly and they are the same, we always would get 0 out of it, because we compared with a 0, it's always true, and because we sum up all these true values, we get to a maximum value of 31, which we would divide with. So we would get a value of 1, and we multiply with 100, so we get an accuracy of 100 if we have the same versions. If we don't have the same states estimations, we would get a lower score. So to run it with our Hamburg model, we can see that we have 77% accuracy. What we can also insert is the Brocken model, which will have a higher accuracy of 80%. And the last one would be Munich, and we hope this will get the highest accuracy. And we have accuracy of 96%, so which is pretty high. And yeah, with that we can have look into our estimation and decode, or we can look in our observation and guess the most likely, in our case, the most likely place where this observation was made. And yeah, that was the first part of this exercise. The last part of this exercise is the evaluation problem. For that you can open the evaluate DIY file. In that you will have again the NumPy include, the sklearn include, and the loading of the data that we provided you with. Those are pretty much the same HMM models, so the Brocken, the Hamburg model, and the Munich model. And afterwards we want to apply or implement the forward algorithm for evaluation problems. For that we, again, like in decode, we have a function where we give the HMM model that we want to analyze and then the observation. What we want to do is we want to look if that observation fits to the HMM model, and we want to look which of those is the closest fit. So for that, again, we have to get our HMM, our A matrix, our transmission probabilities of our HMM model. Afterwards, we get the termination of our transition matrix, the observation models, and we define some dimensions. So we know that our states is the length of b plus 2 for the final and the initialization state. And we know that our t, our time steps, time length is the length of our observation. And yeah, afterwards we go to, we define our forward probabilities, denoted as f. And this is an array with the size of our states and a length of our time steps. And afterwards we go through each of those values and fill in for our f value. At first we go through each time indice, so we go from 0 to t, or t minus 1 in this case. Afterwards, we iterate over each of those states, but we start at the first and end at n-1 state, so we don't have the initialize and the final state. And we initialize this version with this if clause. So if we are in the very first time step, n is equal to 0, and we want to fill in our f. For that, we know, because it's the first state, we want to fill in our f of I state, and our time indices n, so n would be 0. And we know that our transition state has at first, because we're in the first state, 0 in it, and afterwards the ith state. And yeah, we fill it, we multiply this transition matrix with our exponential of b and the rest. Yeah, afterwards we go every time through this else clause. So we know that we are not in the first time step, and go through the other time steps. For that we also loop through all other states. So we go, we build the combination of all of those states. And for that we have our temporary value that we set to 0 beforehand. So we sum up all of those possible paths that we have. So we go again over j, so f of j, the path that we loop in this smaller loop. And for that we go over the n-1, so the previous time step of it. And we multiply it because we are in the current time step with the j and the i's transition state of A. So for that we calculate just every combination of it. Afterwards we want to calculate our forward probability. So again we have our I and n f value. That's pretty much the same as here. And because we summed up all of our current a's with our previously f's, we have this temp variable, and the second part would be again just in this part the exponential of b part. So we have that filled in, and yeah, because this is a for loop, we do it for all time steps and all states, and afterwards we have our filled in f matrix. Afterwards, we want to transition into the termination state. For that, again, we have more or less a temporary probability variable that we loop over all of our states. So we add or sum all of our states up. So we use all f's that we know we are in the ith state, because we loop over all I states. And because we know we are in the final state, we know that the previous state is the t-1 state. So it's the final state -1, so the last state. And as a termination criterion, we also use the n-1 state, because we know that we are in the second to last state that will lead into the final state. And for that we all insert all of our states, because we end up in the final state. And yeah, that should be the evaluation function. Now we can test our implemented function, and we load some of our observations. So we have 3 observations, observation 0, 1 and 2, and we want to use those and look from which place they probably are. So to test that, we can at first look at the logarithmic of the output of this. So we know that this is a probability, and we can just calculate the logarithmic of it and have a look at that number. Evaluate, we have to run evaluate, of course. Now we know evaluate. Afterwards we have to run, of course, observation data, and now we can run the logarithmic of it. So yeah, we have a pretty low result, -350. We can test it with the second version. There we have a higher number, around 70, and yeah, this will give maybe a small hint if this this HMM is fitted for these observations. So in the last part, we can now determine the origin of the observation. For that, we can load some of the observation in. For this example, we load observation 2. We know that our given observations are the Brocken, Hamburg, and Munich. And these have to line up with the first 3 versions of it. So this had to be the Brocken, Hamburg, and Munich. Otherwise, we would get wrong results. Afterwards, we can calculate the probabilities for each of those models for the one observation. And we will get 3 probabilities, and we can compare those probabilities with each other. We can calculate the logarithmic of it. So if we know that the first, now we can fill in the question marks, and this is a little bit to think about. If the probability of version 0, so the Brocken, is divided by the Hamburg version, and that result is bigger than 0, we know certain things, and afterwards we can use this again if the P0 is divided by P2, and this is bigger than 0. We know because we calculated, we divided those and calculated the logarithm of it. We know that the highest probability is the Brocken, so the P0 of it. In the other case, we know that the Brocken has a higher probability than Hamburg. So the Brocken is more probably than Hamburg, but in this case it wouldn't be as probable as Munich. So in this case it would be a 2 for Munich. And in the second else if we can fill in the other version, so this would be P1 divided by P2. So if this is greater than 1, we know that P1 is more probable than P2. In this case, the result would be 1. And if this is not true, we know that's the last case that can happen, that P2 is the most probability version. So this is pretty much the else case from this if line, but maybe in this case it's the other way around, so we won't end up in this case. Yeah, and if we run this, we can look into that the model 2 that we used is most likely from Hamburg. We can play around a little bit. If we insert 0, it's most likely from the Brocken, and if we insert 1, it's most likely from Munich. Yeah, and I hope this explains or shows some of the power of hidden Markov models, and maybe you can apply it in some future problems by yourself. Yeah, goodbye.